So Pascal's principle, the first thing that we're going to be talking about, is basically just to do with pressure. Pressure is force over area. Like that. So this is the idea. There is going to be a lot of pressure here on the tip of the pin. There is less pressure at the top. If you compare the area, this has a bigger area, this has a smaller area. That's what pressure is. Alright, so Pascal's principle is to do with not just pressure, but pressure in a liquid. He found that if you have like a bucket of water, and then you would if you put a plunger in and you try to push this bucket down, and you were trying to push the lid, push, the water will not crush anymore. The water will not get smaller. What actually happens is the water ended up making a little hole down here, and the water came out of the hole. And then he realized by applying a pressure down here, it pushed the water through a little pipe. So then he decided to take this pipe and he will open up another little place. And he says, what would happen then if I was to put something here, push the water down on this side, what would happen on this side? He found that by pushing this down, this moved up. He realized that he was able to push this little part and move this side up because water cannot be compressed. So then he came up with a little principle. He realized that the pressure on both sides was the same because it's the same water. So that takes us to Pascal's principle, which is pressure 1 was supposed to be equal to pressure 2. And we know that's F over A. So the first force and whatever the area is, I'll call it F1, A1, it will be the same idea as F2, A2. Now what he found was that I can have a smaller area and I can have a bigger area. I can lift big, heavy things with something quite small. I can use my own hand to lift up a car using a car jack. By applying a force on this side on a small area, I have a bigger pressure and it will translate over to the other side. Let's take this into our first question. We have a question over here. He raises his customer's chair by applying this force to a piston of a small area. So I can use this picture from question 3 to help. He applied a force, I'm going to just point it over here, of 150 newtons. He applied this force and my area was 0.01 meters squared. And then there is a chair on the other side. That area was 0.1 meters squared, so a little bit bigger. He wants to know how much he can lift on the other side. We have a mass of the chair, we need the mass of the customer as well. We'll get out to the mass in a minute. Let's just figure out how much force that would be. So first things first, I will do the formula. I've got it written here, so I'll continue from here. I will do 150, I'm going to divide that by my first area, 0.01 equals the new force that I want to lift. I don't know what this force is going to be, so that is my X. I will just call it X, or whatever. And then I'm going to divide that by that area, 0.1. We will cross multiply, shift solve, whatever you like. That will tell me my actual force. So let me do that first. What do you get when you do this? Let's give this a try. I'm going to 150, 0.01, multiply by 0.1. I should get a force of 1000, x equals 1500. Did I get that correct? Very good. So now I have this force. Fine. But this is not asking for force, it's asking for mass. So we know from grade 9, W equals mg. That's gravity. So m is simply going to be W over g. I can lift up a total mass of 1500 over 9.8. That's the total I can lift. Let's find out how much that is. Divided by 9.8. The total I can lift is 153 kilograms. Okay, fine. So now the thing is, the chair itself is 5 kilograms. It's a heavy chair. So the final step is simply just going to be 153 minus 5 kilograms. That leaves me with 148 kg. And that's why our answer will be here. So what did we do? We applied Pascal's principle. I seen a force in an area and another area. So this is the rule that I decided to use. I calculated the force, and then I found the weight, because force is the weight. It's the same thing. Weight is a force. So I rearranged it to get mass, found the total mass, and subtracted the chair. Now looking at this one here, we have a hydraulic system. Again, we're lifting a mass. I can turn that into a weight just by using mg. I have a mass lifted, and I have an area here and an area here. They're both in meters squared, so no need to do anything. What is the minimum force applied? Okay, so same thing. F1 A1 equals F2 A2, like that. So we have to combine. So this lift, this hydraulic system, this vehicle is on this area. Usually the bigger mass is on the bigger area. So these two are together. So I can consider them together. I can put it on the left or I can put it on the right. It doesn't matter. Before I do that, I do want to convert that. I don't want to have kilograms. I'm just going to do W equals mg.
mg.
Yep. So I'll just do 2000 and I'm going to just times that by 9.8, which is
19,600.
1960. Perfect. Newtons. Perfect. Let's do that now. So I will just put it on the left side just to see what happens now. 1960. And I'll divide that by my
Mr.
area.
Double zero.
Oh, 00. Yes, yes. 00. Thank you. 19600. Thank you for your support. And that's the area, 0.5. Equals F2. That's what I need. I will name it X. I can leave it as F. And that's my new area, 0.03. So again, cross multiply, whatever, you'll get your final answer of, hopefully, 1176, exactly. So checking that, you can check yourself. The answer is C. All right, so now let's just clear off this stuff here because that was related to the previous question. Question 3, what does this one say? And what is true? The pressure at 1, 2 and 3 are the same. Actually, that's what I mentioned up here. He found the pressure was the same everywhere. We've actually already got our answer. The other ones are going to be wrong because it's saying the pressure is different. 1 is greater than 2, 1 is greater than 3. No, because pressure is the same throughout, which is why I can lift a big force with a small force. A is the answer over here. Archimedes' principle. Archimedes' principle is just about flotation. Some objects float and some objects sink. You might have seen those videos, will it float or will it sink? You throw like a ball inside, what happens? You throw a big rock inside, what happens? Some of them stay, some of them don't. There's a force pushing up. And it's related to the density of the material. The density, which is written as a lazy P, rho. And this is how we can figure out densities and things. What it means is how close together the stuff is inside. If there is not that much stuff inside a ball, like a very, like an empty ball, it will float because it's less heavy than the water. The water is heavier, more dense. But if I have a rock and there's a lot of stuff inside the rock, it's a big heavy rock, it is heavier than the water, it will sink in the water. That's the idea. So Archimedes' principle, just FYI, came about a long time ago. There was a king who had a crown. Well, he didn't have a crown. He had 1 kilogram of gold. He had gold. He went to a goldsmith and says, I want you to make me a crown with this kilogram. And the guy did it. He made him a very nice crown. This is my attempt at drawing a crown. Maybe it looks like this. And then he placed it on a scale. And on the scale, it said 1 kg. And the king was very happy. He took it home and he was wearing it. He was at his in his castle, and then eventually he realized, what if he's lying to me? What if he stole some of the gold and he replaced it inside with maybe iron or something and just covered it in gold? How would I know? The weight is the same. I would have to break this crown to check, and I don't want to break it because what if he is not lying? Maybe it is gold. So he calls Archimedes, his friend, and says, listen, I have a crown here. I want you to tell me if this is real gold, but you're not allowed to open it. So Archimedes spent a long time trying to figure it out. How am I supposed to do this? How to find whether this kilogram is gold? He couldn't figure it out. So he decided to run a bath. He got inside a little bath. They used to have big blocks, and he filled up the bath with water. He got into the bath and the water spilled out. He shouted, Eureka! This is where the term Eureka comes from, if you've ever heard of that before. It means, I've got it. He figured it out. Just because the water spilled out, he figured it out. He ran all the way back to the king and says, I know exactly what to do. He pulled up a little beaker or a big thing with water and another one. He said, here is a kilogram of gold. He dropped the kilogram into the water and some of the water spilled out. He caught the spilled water. This much water came out. But then he did the same thing with the crown. He dropped the crown into the water. And then what happened, maybe you can guess, less water came out. That means the material inside was less dense than the water. It cannot have been gold because gold replaced this much water. That's the volume of water the gold displaced. The volume of water, I made that too big, the volume of water that this displaced was less. This volume was less. And then he told him, and the king opened up the crown and found out that yes, there was other materials inside. So he found the person who did it for him, and that person was never heard from again. You can maybe guess what happened to him. All right, moving back onto the thing. Which is the thing that's a condition for an object to float? Well, I just mentioned it, that the weight of the object, if it's going to float, it should be the same or less than the actual, what's it called? The water itself, the density of the water. So, we're looking at this here. Weight of the object is equal to the weight of the displaced liquid. That's what I just mentioned here. If I have an object floating, the weight should be equal to whatever this is. If I measured this, if I took this and I put it on a scale and I measured the weight of it, that would be actually the weight of this object. It's pretty cool stuff. So that is the idea of this, the first part of the principle. It's a little bit more. So if the weight was greater than the buoyant force, by the way, if the buoyant means upwards force, the buoyant is a force pushing up in the water. If the weight is greater than the water, of course, it will sink. Moving on, checking out this here, now we're going to apply a little bit of Pascal's principle, not Pascal's principle, the other guy, what's his name? Archimedes' principle. There is a force, there is a pressure, there is an area, we have a volume, we have a cube. Basically, this cube is sitting inside this little block. This cube is inside the block, but not fully submerged. So now half of it is submerged. It's not displacing the full amount, it's taking out some liquid. All right, if we can figure out the volume of the liquid, maybe we can find the pressure. We can find the pressure with knowing the density of the water. Rather than doing W equals mg or having to use like a scale, we can figure it out with volumes. Long story short, there is a formula associated with it to find the pressure for this, or to find the force, I should say, not the pressure. We're asking actually to find the force. That's easy. Force, we can do, I think it's rho Vg. I believe that's the rule. I forget myself. I will check the formula sheet in a second. But the first thing is we should know the volume and I should know the density. So let's see if this works out. This is a cube. So I have a cube. So you would normally think a volume of a cube is 1 times 1 times 1. But in this case, not all of the cube is submerged. So what I'm going to actually have to do is I'm going to have to do 1. So the volume of whatever submerged will be 1 times 1 times, so 1 and 1, 0.5. 1 times 0.5. So that would just give me 0.5 meters cubed. Is that right? Yes, that's right. So then I will know that water has a density. You will check this in the constants. The density of water is 1,000 kilograms per meter cubed. 1,000. So if I was to do this, I hope I get this right. Rho Vg, I'm going to bring that over here. 1000 multiplied by volume 0.5 multiplied by 9.8. Let's check to see if I got that right. 1000 times 0.5 times 9.8. I got 4000. Perfect. So yes, this worked out nicely. 4,000. I never doubted myself for a second. I knew it. So 4,900. Of course, it's rounded up to 5,000. Rho Vg. That's the rule for this idea. That's the good thing about physics. You don't have to memorize things. You just learn something, and then if you know the rules, it will stay forever in your mind. I haven't done this for like 8 years. So that's a good thing, unless, you know, there's things you have to learn, specific words and things like biology and chemistry. You need to learn things. Physics, you just know the logic and you will be able to get the answer. That's why physics is amazing. Right, what's this? We have an 8 kilogram object. It's falling down, not falling down, but it's in the water, but the reading is 60 newtons. So, of course, as I mentioned up before on the previous page, there is an upward force. Well, it's right there. The buoyant force pushing up. The water pushes up. You probably know this if you ever go to the pool and you try to get like a beach ball or a ball and you try to push the ball into the water, it flies up. I know W equals mg. We used it earlier. So that's 8 times. I'll stick with 9.8. If I round it, I round it. And you know what? Actually, it looks like this. It's not rounded. Let's do 8 times 10. Let's make gravity 10 just to see what they're doing. That's 80 newtons. Fine. The weight of this block should be 80 newtons. However, because the result, the reading is 60, so we can say that the reading will just simply be 80 minus 20 equals 60. That's the resultant force. How did I figure that out? Well, what I did was I did a little free body diagram in my head. I did my W and I realized that was 80. And then I had a upward force, a smaller force, and that said, well, I didn't say anything. That's what I'm trying to figure out actually. It said my resultant was 60. If you want to write it as a formula, it's literally just F1 plus F2 equals F net. This is as a formula, F net or F total. F net is 60, that's the reading, so that all equal to 60. This is me doing it as a formula. The reason I'm showing you this is because another example might not be as simple or clear. So this is the general formula for the forces. F1 would have been my weight, and then my F2 would have been the buoyancy force, and that's why I substituted in 80 plus or minus, it doesn't matter, will be whatever my force was equals 60. Rearrange, and yeah, the answer is 20. Okay, so based on what I've said so far, why don't you help me here? Question 7. Which of these do you think... Oh God, the answer's there. Don't look. Okay, now you can look. Which of these is the best to find the weight of a body in the water? I hope you didn't see
The third one.
Is that because you...
The weight, but it's...
Oh, I heard a second voice. Hello, second voice.
No, Mr.
Hello, how are you? Why the third one then? Tell me why. What's the problem with the first one? Here, down. What's the problem with this one? Why is this not good? There is not just one force here. Basically, it's touching the bottom, right? Which means the bottom is pushing up against this block. It's the full amount of liquid is not displaced. The ground is supporting, the bottom is supporting it. So that's not good. Over here, question 2, you can see that it's floating. So not all of it is inside, which means not all of the water will be displaced. As I mentioned earlier, if I weigh this, if I put that on a scale, the liquid displaced is the weight that we have put in. But if it's not fully submerged, that's not the full weight. So that means the last one is the best one. Okay, the last one being the best one because the full block is inside, all of the volume is displaced, which means I can figure out the weight of this one. I can find the mass and do W equals mg. That's why it's the third one, so this is good. So then we're talking about an object to float, same thing. So I mentioned that, I think that's pretty much the same as down here, condition to float. It's the same thing, is it the same question? It's the same question. The weight of the object is equal to the weight of the displaced liquid. If the weight was greater, it will sink. So that's why we have the displaced liquid idea. So it's the same as the previous question that we did on the last page. Now we're moving over to Bernoulli's principle. Bernoulli's principle is to do with the speed of the air and the pressure associated with it, and just the type of flow. We'll start with the type of flow. You see there's a little thing blocking liquid, water flowing. There's like maybe a pipe. It's smooth, nice straight lines. Smooth flow, smooth straight lines. This is, I will call it smooth because, well, it's smooth. And there's a name for it. This smooth, that's a T, is actually called laminar. Laminar. Smooth is laminar. That's an R. Okay, and then it goes to the ball, and then the water starts to move around, the liquid will start to go, it could even be air, whatever. It becomes crazy. This is not smooth, not smooth. It's not smooth. And of course, there is a word for it, and the word here is turbulent. 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 My guess is you've probably not heard of the word laminar before, or you may have, but you probably have heard the word turbulent before if you've been on a plane. You talk about turbulence and the plane starts to shake, and they say we're experiencing some turbulence. If you have, that's this. It's basically the air around the plane. The air around the plane is not smooth, so the plane starts to move around a little. It's safe, it's just a little bit uncomfortable. It's like a bumpy road. So now, what am I saying? Which is true from A to B? So it went from smooth to not smooth. The liquid is in laminar, non-steady flow. Well, it's not fully laminar, so that's not useful. It started it, but not at the end. There is a transition. Yes, it went from laminar to turbulent. It went from laminar to turbulent. So I agree with this one. This one's good. There is a transition. From turbulent to laminar? No. From laminar to turbulent. 2 is the best answer. So now we're talking about water flowing from one side to the other side. So we're going to talk a little bit about pressure and speed and things like this. Before we mention that, there's a few things you need to know about the actual general idea. If you have, how would I say, like an area and a speed, or a distance and a speed, you will notice that we have a narrow pipe and a big pipe. A narrow pipe, we will have, less space for them to flow. A big pipe, there is more space to flow. So that means there is a change of speed. And the same thing over here when we talk about these. I will go through each thing one by one. So we need to know that there is going to be a slight difference. There is a few formulas associated with it, and we'll get through them. So the first things first, what's happening here? Over here, at this point, the speed is 4 meters per second. 4 meters per second. Over here is 2 meters per second. 2 meters per second. Now, if you ever have like a garden hose or a pipe, and you get the hose, and then you're spraying the hose with water, and then you decide to cover it with your finger, the water shoots out faster, and you can shoot it further away. That's this idea. This Bernoulli's principle. It's the same idea here. If there's a smaller space, it will move faster. It will move much faster, more kinetic energy, but because it has more kinetic energy, it will have less pressure. Because the total energy, you have pressure energy and the kinetic energy, they add up to the total energy. That means if I am moving faster, this must decrease in order for me to have the same total energy. If I am moving slower, I will have less kinetic energy, more pressure energy. So that's something to just think about in your mind. They are related to each other. Why did I raise that? I need that. Okay, now I'm supposed to figure out the difference in pressure. So before I decide to figure out what the difference in pressure is, I need to know the actual formula for pressure. That would help, of course. So that means what I'm going to do is think about the formula. This is Bernoulli's principle. I think, if I remember correctly, the pressure is a half P, or rho I should say, the density times by the velocity squared. You don't need to memorize it. It is given to you in the equation sheet, so you'll have it somewhere. We have 2 speeds. So technically, I have 2 pressures. I would have to calculate the difference by simply subtracting them. I will do the first one minus the second one. So I can do this minus this, or if you want to be smart, what you can do is you can find the difference in pressure is between these two are the same. This is the density of the water, the density. That's P for pressure, that's rho for density. Let me just make it clear. That's P for pressure, that's rho for density. It's a lazy P, it's just basically a P falling over. That's what I'm trying to write over here. Let me try that again so you don't get confused with what looks like two P's. It's like a lazy P, a lazy P. You can do a half lazy P, and then you can take away the two V's, V1 minus V2 squared. You can do it that way. You can solve it and you will get the answer for P. I'm actually aware that I'm taking too much time, so let me see if I can speed up a little. So if you don't like doing that, you can just go ahead and solve the first one, subtract the second one. You will get your same answer, it's not a problem. 1 over 2 multiplied by 1000 multiplied by the change in the speeds. So final minus initial you can do if you like. 4 squared minus 2 squared, and you should get, well, I'm assuming you'll get 6,000. 6,000 pascals.
Yes.
PA, right? And the answer is D. Now, this is talking about what I mentioned here about the pressure and the speed. So we need to know a few things according to this. Which of the following is true according to the principle talking about the pressure and speed? So, first things first. Where will it be faster based on what I said before? V1 or V2? Which one should be faster? We would say V2. If you squeeze it, it will move faster. Just like the garden hose idea, you can give it a try. If you squeeze it, V2 is faster. So this is faster and this is slower. And already I can see V1 is less than V2. Actually, that is nice. Okay, let's compare pressures. If it's faster, it has more kinetic energy. What about the pressure energy then? Will that be greater or less?
Greater.
P plus K equals total. Let's make up some numbers. 50 plus 50. I'm making this up. 50 plus 50 equals 100. Very nice. Now, what have I said? I have said my speed is faster. Kinetic energy, a half mv squared from grade 10 term 2. V is going to be bigger, so the kinetic energy is bigger. So that means I will have to have it equal to 100 still. Total doesn't change. Total stays the same. Conservation of energy. Maybe I made this 80. What happened to my pressure then? What must this become?
Yes.
Less, maybe 20, right? So the idea is K will increase, the P will decrease. So that means my speed is bigger, my pressure is less. I won't put the arrow there, you might get confused. Pressure is less. So my speed is less, so my pressure must be
Higher.
higher. High pressure, low speed. High speed, low pressure. This little thing you can write for yourself to help you for this idea. Okay, P1 is greater than P2 or P1 is less than P2. I've drawn the arrows already. You can see that now. P1 is greater than P2, right?
Greater.
1 and 3. Let's hope I'm right. Whew, okay, I am right. I did not doubt myself at all. Very good. So that is why the answer is C. Water flows from left to right through 5 sections of the pipe. Where does the water speed increase, decrease and remain constant? And I can see that there actually is no pipe here, but 4 or 5 years ago I did see this in an exam question. Because I have perfect photographic memory, I know what it looks like. It went from something like this. We had a big pipe, and I am making this part up now, so I will call this A. It goes to here, and then it will go maybe a little bit bigger again, so this is B. And then I went to C, and then it went to maybe bigger again, D. This is D, and then we will say E. Now the problem is, my photographic memory, the film has run out, so I have no idea if this actually is the same thing, so I cannot use these. But what you can do is you can help me a little. I'm going to extend it a little because I've seen constant E and then F. From A to B, does my speed increase or decrease from A to B? You tell me.
Increase.
So A to B increased, okay. And then from B to C, tell me.
Increase.
B to C, it decreased. I hope you said decreased, right? C to D, what happened?
Decrease.
Decreased again, okay. And then you get the idea now. D to E,
Increase.
increased. And E to F,
Same.
it stays the same because it didn't change. E to F, constant. That's the idea. So you would take whatever you have here from the picture that they gave you and find the options, whatever's going on from A to B. You will know what's going on. So the picture's not there, so I'm not sure what's going on. Okay, so now we have this. Now we have, what's this? Let me zoom in. Airfoil is an application of Bernoulli's principle. This is fine. What's happening here is airfoil being lifted. Now this is actually quite interesting. You can do this yourself with just a piece of paper. I have a paper here. If you take a paper and you hold it in front of you and you just let it flop in front of you like a pizza that's falling down and all the cheese is about to come off, and you blow the top of the paper, which way should the paper go? Should it keep going down even more or should it come up? I am holding a paper in my hand and the paper is falling down. That's my paper. And this is my face. That's my nose. And that's my eyes. That's my eye. That's my hair. That's my head. This is my ear. I have a big chin apparently. And I am blowing. If I blow it, what will happen to my paper? I look terrible. Anyway, if you blow through it, if you blow on top of the paper, not the ball, the paper straightens up. Why? Let me try again. Yes, the paper straightened up. Why did that happen? I hope you understand the actual question because this picture is absolutely horrible. I'm going to delete that picture. The reason why something that happens is because the air above the paper was moving faster than the air below the paper. Remember, faster speed means less pressure. Faster speed, less pressure. So if it's moving faster, I will have less pressure. If there is air underneath, it will push it upwards. Let's apply it to like a wing of an airplane. We have air flying. The plane is flying at the same constant speed. So the speed here and the speed here is here. And look, this moves a little. Now, the distance here and distance here is whatever the distance is. It's not important. But the point is, the time it takes for it to get from one side stays the same. So in order for that to be true, this has a bigger distance to travel than this, which means to reach this side at the same time, because this is going to reach here at whatever I decide, this has to travel faster. The air on top of the wing has to travel faster than the air below the wing. The speed is smaller. So now you can probably guess then, if the speed is faster, the energy for the kinetic energy is faster, the pressure is less. If the speed is slower, the pressure is more. Which means, if that is the case, I have more pressure underneath than I have on top. This will point overall upwards. The plane will stay in the air. The plane will fly up. To travel this bigger distance in the same amount of time, it must be faster. If it's faster, then the pressure will be less. And that's why we're picking air above the airflow is faster. Pressure at the bottom is greater. The pressure difference, small pressure at the top, big pressure at the small, the difference in pressure causes it to lift.